Okay, check those cell phones into their hotels if they're not, and let's jump into this. Okay? Now, some terminology, and then we'll talk about how to do it. So when electrons share, the way that it works is that it's always kind of, well, it's both ways. So it's like, I'll share one with you, you share one with me, that makes a bond, and now they belong to both of us. So chlorine has 7. So when 2 chlorine atoms bond with each other, it's because they're sharing one with each. Now the way that we draw a bond is by, so draw this picture up next to that one, is with a line in between. So a line in between signifies a bond. When there's just one line, we call it a single bond, and it represents 2 shared electrons. The ones that we draw as dots, these ones, these are what we call a lone pair of electrons. So for chlorine, we would say it has 1 bonded pair and 3 lone pairs for each of them. Okay, now so this is a single bond. This right here is a double bond. Double bond means they're sharing 4 electrons between them. This right here is a triple bond sharing 6 electrons. Now don't say it out loud, but I want you to think about why this might be. There is no such thing as a quadruple bond. It doesn't exist. So think for 1 second why that might be. Why would a quadruple bond not exist?
For a million.
Okay, Ben, let's have you share with us. What are you thinking?
So I was thinking because these are metallic, that's what metals do. They share all of their electrons.
Ooh.
Like these are kind of covalent. They can't share all of their electrons, that sort of thing.
That's an interesting thought. I've never thought of before. In a sense, though, carbon can do this and share all of its electrons on different sides.
Okay.
But not a bad thought. Not a bad thought. Any other thoughts? How's smiley face for sharing, Ben? Yeah, Josh.
Is it because, like, you know, for it to share, the electrons kind of have to be in that area, and if there's like 8 shared electrons in that one spot, then it's like way too much for it to handle, way too much negative.
Yeah, what happens here is the length of the bonds decreases as you have more bonds. So a triple bond is shorter than a double is shorter than a single. What are we pulling closer and closer together as the bonds get shorter? The nucleus, right? So the nucleus gets too close,
And then that will make it go.
right? So we have this problem of too much overlap. It just doesn't work, at least to this day. Who says it won't one day? Scientists may find a way in which to stabilize a quadruple bond, but as of right now, they're not stable. They rip themselves apart. So, yeah.
How are
Ben.
the nucleuses going closer, like force them apart because they're both positive and positive, like is forced apart? Oh yeah, never mind. Sorry.
No, you just answered your own question. You're good. You're good. Sometimes saying things out loud answers your question. So, Greg, did you have a question?
No.
Okay. Yeah, Matt.
So on the 2 nitrogen atoms,
Yeah.
how the 2 outside electrons are bonding with each other, how does that do anything?
So, great observation. So this is, it's just a format thing.
Just to make it look or something?
They aren't actually bonded. They're lone.
Yeah.
You can draw lone pairs as a line if you want. I prefer to draw them as dots to signify the difference. But it means, so this means the same thing as this. So, no, good observation though. Okay, I'm going to show you the rules so we can fill them in, but then we'll walk through examples. Okay, so here are the rules. Sorry, it's weird pink.
Wait, what?
Ow.
I'm sorry.
My eyes are dead.
Okay, so fill this in your notes really quick, and then we'll do some examples. So as we do Lewis structures, these are kind of the steps that we'll follow. Once again, we'll do 3 examples together. I just want you to have the rules down so you have reference of something to go back to. So the first thing we want to look at is how many valence electrons everything is coming to the table with. right? Because you can't use more than what you have, and you can't use less than what you have either. If the molecule has a charge, that obviously changes how many electrons you have. It either adds or subtracts depending on the charge itself. The first thing after knowing how many electrons everybody has is you then figure out, all right, which one is considered the central atom and who are the exterior atoms. The one that goes in the middle is the one with the lowest electronegativity. Another simple way is if there's only one of them and multiple of the other, that's the one that goes in the middle. But that's the hard rule, is the one with the lower electronegativity. Okay? Why do atoms bond in the first place?
To become more stable.
What does that mean, Matt? Like, so good, Andrew. That does become more stable. How do they become more stable, Matt?
By filling their electron or their shells or orbitals
Good.
completely.
So to become stable, we need a full shell. You guys can both have a smiley face for that. So keep in mind, like, this is the goal. If this doesn't happen, that molecule may not even exist. Now, once again, there are going to be exceptions to this. Okay, the octet is more of a guideline than even a rule. But that is the main objective, is they're trying to complete that shell. Yeah,
So
Connor.
why is a full shell more stable than an incomplete shell?
In terms, so when we use the word stable here, we're referring to the chemical reactivity.
Yeah.
That when it has that full outer shell, it doesn't react with things anymore.
Okay.
And so that's what we mean by stability, is it's not reactive.
So you know how there were like electrons in between the atoms because they were being shared, and then there were electrons around the atom? Like,
Yeah.
does it matter like where they go around the atom?
In terms of completing an octet, and we'll draw a bunch of pictures here in a second, Sam, no, it doesn't really matter. It's just kind of depending on how you draw it. So, okay, let's do our first example. So we're going to draw a picture of the molecule PCl3. So the first thing we need to do is know how many valence electrons they each have. So how many valence electrons does phosphorus have?
5.
Chlorine has?
Seven.
Okay. If you don't know how to find that, we need to know how to find that. Okay? Also, Lewis structures, guys, should be something you become super awesome at. This is like, so there's things in AP that are like problem solving. We don't know what to do and we have to figure it out. Lewis structures are not one of those things. It's a skill, and once you learn that skill, you should be able to master it every time. Okay? All right. Now, between phosphorus or chlorine, which one has the lower electronegativity? Phosphorus does. So phosphorus goes in the middle. We have 3, because my formula right there, we have 3 chlorines around it. Okay? Now, we typically place them in some sort of T fashion or plus sign idea, but where is up to you. So you can do Cl, 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 like that doesn't matter. So I'm just going to go like this. Oh, side note, I would always do Lewis structures with a pencil, because there's a good chance you're going to be changing things and then your picture will look like cleaner. Or if you're using pen, then just draw me a cleaner picture when you're done with your work. Because if the work is messy and it's hard for me to see, you want to make sure you have a clean picture. Okay, chlorine each comes with 7, so draw 7 around each of them. 1, 2, 3, 4, 5, 6, 7. Phosphorus comes with 5. So build your skeleton, add what they're coming to the table with. Then you always start with single bonds first. Okay? So chlorine shares with phosphorus, phosphorus shares with chlorine. Those 2 electrons become a bond. Okay? Do the same thing on all sides. After you've done single bonds, check to see if they have their octets. If they have their octets, you're done. If they don't have their octets, then we have to look at a double or a triple bond. So I'm going to draw some circles just to like show, but the circles aren't like part of the Lewis structure. So this chlorine has 2, 4, 6, 8, because the line counts as 2. So he's good. 2, 4, 6, 8. Check. 2, 4, 6, 8. Check. 2, 4, 6, 8. Everybody is happy, meaning we must be right.
And we all get a smile.
8 electrons. Calvin, did you have a question?
Yeah, so how did you guys just know that single electrons you know what I'm talking about? Because there's 7 electrons here,
Uh-huh.
you put the 1
Oh, okay. I kind of knew the end goal in mind, so that kind of helped. I'll show you an example of if you don't know, and then how you can clean up your picture in a second. So, okay, good so far?
Yeah.
Okay, let's do this one. So HCN. Okay, first off, who's gonna go in the middle of this atom? So, I will agree, everybody, that hydrogen does have the lowest electronegativity, but hydrogen can't ever go in the middle. Why? Yeah. It only has 1 to share. It can't go in the middle because it can't share more than once. So hydrogen will never go in the middle, so then we go to the next one, which would be carbon. Okay, so I'm going to put carbon in the middle, I'm going to put H on one side, I'm going to put N on the other side. That doesn't matter. You could put N and then H. Okay? All right, give them what they have. So 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay? And then draw your bonds. Okay, so single bond on this side, single bond on the other side. Start with single bonds first. Now check your octets. Does hydrogen have its octet?
Yes.
Yeah. Hydrogen's octet is only 2, right? So don't do anything to hydrogen. That's good. Does carbon have its octet though? No. And neither does nitrogen. Now I always focus on the outside ones first. Make that and then worry about the middle. So we need to add another bond here. Nitrogen happy yet?
No.
Nope. So draw another one. What about now? Good. Okay, now let's redraw it in a cleaner looking way. So my answer would be HC triple bond to N, and then you always, any lone electron should be brought into pairs. Now where that pair is placed doesn't matter, but you don't leave them separate from each other when they're just dots. Questions on that? Once again, if you check your octets, good. Carbon has 2, 4, 6, 8. Nitrogen has 2, 4, 6, 8. Everybody is happy?
Another smiley face?
Don't pronounce it.
You guys are really good at helping each other. Yes,
I
Sam.
don't know if you just answered it because I was like looking at something.
Yeah.
But why can't those two like be a bar?
These ones right here.
Yeah.
First off, they don't need to. Once they both have 8, stop bonding. Right? So since carbon has 2, 4, 6, 8, we don't need to make any more bonds. So carbon also, if you look up here, Sam, carbon has ran out of electrons to share. Right? So, yes, Eli?
So, just kind of thinking on top of my head here, let's say you have like something like that, like aluminum and oxygen 3, would aluminum be in the middle because you can't? Would it just be like that?
So why were you, did you say to
for
put,
an example, if I have like aluminum and oxygen,
yeah.
you would put aluminum in the middle, right? Even though it's more.
Well, you can't even do these with aluminum.
Yeah, first off, this is a hard example because aluminum's a metal actually, so it doesn't.
Or like something like that.
Boron.
Wait, well, no, that is, like chlorine. If you have chlorine, you have 3 oxygen, oxygen.
So a simple way too is if you ever have multiple of something, so like in this one, since I have 3 oxygen and 1 bromine, the bromine's gonna go in the middle. If you have multiple of something, the single thing always goes in the
So
middle.
like, what if you had like bromine 2, oxygen 3, like, how would that be different?
Oh, good question. That's a case where you would have more than one possible central atom, which we'll get to later. So hang on to that question for a little bit. So, okay, here's my skeleton, everybody. Eyes up here. Okay? Because it's like kind of boo, is that why? Or just brew? Okay, so give them what they have. So 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7.
Isn't the oxygen minus?
Good. Everyone circle that minus right there. That means what?
That means that we
It
have
has added one more electron.
Ooh, we just have one electron total. So minus 1, because it's O3 and the negative is supposed to be exponented.
One electron.
So we have a bonus electron to add to our picture. Just one. Okay? 2 minus would be 2, 3 minus would be 3. Now you add the bonus electrons, this is now the opposite of the other rule, to the one with the higher electronegativity. So in this case, so it goes on one of the oxygens. Now which oxygen doesn't really matter. We'll talk about like kind of the end picture. So I'm just going to add it here. Okay? So if you want to maybe make a note or something, right? That's our bonus electron because of the charge. Now if it was positively charged, what would that mean? Then we have to remove an electron. Okay? Okay, let's bond. Single bonds, start there. Okay? Now once again, focus on the outside atoms. Does this oxygen have an octet yet? Nope, because it has 2, 4, 6, 7. So it needs to bond again. Okay? Does this oxygen have an octet?
Nope.
Nope. 2, 4, 6, 7. So we got to bond again. Stay with me here, people. Your eyes are getting wider by the second. I know it's a little weird. Okay? Okay, does this one have an octet though? Yeah. 2, 4. I'll move this guy over here. 6, 8. Good. Okay, I'm going to redraw it so it's cleaner looking. So we have an O double bonded with 2 lone pairs. Same thing on the bottom. Double bond, 2 lone pairs. Single bond, 3 lone pairs, and then the bromine has 1 lone pair. So that's just that cleaned up.
Bromine has like 12.
Okay, so this is where it looks weird. All of our oxygens have a complete octet, right? But bromine has 12 electrons around it, right? Now, this is where, once again, in earlier sciences, sometimes they tell you things that aren't entirely true because you don't have enough understanding to know better.
Isn't there a way? Sorry, I didn't know my shoulder. Isn't there a way to have everybody have a negative?
But that's not how it exists in the world. This is how it
Even
actually
though it's
exists.
possible, like bond everything.
Yeah, just because you can draw it on paper doesn't mean that's how it exists in the world.
So how would I know like this isn't right because everything?
Because if
else
you
in that-
follow the bonding rules, this is the only way it works.
So since PR is the most electro.
It goes in the middle, yep. And then the options are only coming each with 6. And so they each need 1.
So going down spectrum left to an why would you start again?
The least the one that has the lower electronegativity goes in the middle, right? Because if bromine is 2 rows down from that makes it lower than 1.
Let's say oxygen so height and width.
It's not exactly the same.
I don't have that.
You don't have to. This is a simple way, is if there's a single one, that'll fall. So if it's hard to toss up, you should be able to do that. So, okay, let's talk about this, everybody. So, often when you first learn about atoms, if this sounds familiar, you weren't wrong. There's just a part that couldn't be explained yet. Okay, so you always say, all right, the first shell can hold 2. The second shell can hold 8. The third shell can hold 8. 8, 8, 8, 8. That's what you often learn. But the shells can hold more than 8 because of the D and the F shells. So bromine has what is known as an expanded octet. It can hold, because the D shell, the 3D, because bromine is all the way on the 4th row, it can expand and bond with that 3D shell. Now, not all atoms can do this. Things that are only on the S, or the 1S, 1S, 2S, and 2P can't do expanded octets. They don't have a D shell. But anything from the 3rd and above have the possibility of doing this. Okay? So kind of the rule that we use is starting at phosphorus, because those are metals, so they don't really covalently bond anyways. Starting with phosphorus, anything phosphorus and up in atomic number, so 15, 16, 17, so on and so forth, up, can do an expanded octet. Anything smaller than phosphorus cannot. Oxygen cannot have an expanded octet, it's too small, it can't expand. Yeah, Matt?
Can we have like a visual representation of this?
What do you mean by visual representation of it?
I don't know.
Oh.
How do we show the atomic configuration?
Shows you
Oh, yeah. How does that configuration work?
So what do you mean by like overlap and like combine together with it?
And
Okay, if this confuses you more, I'm
just
sorry.
wondering, can like bromine bond with 8? Can bromine have 8? Like let's say, can bromine bond with 8? Like an 8 neutron shell?
Yeah, totally. No, bromine can exist in a lot of different ways. Like in this case, it's 12. In other cases, it could just be 8
So would they both be stable?
in their own way. Yeah.
Which would be more stable?
I don't.
Like if bromine could choose between 8 and 12 electrons, what would you choose?
I'll have to look into that before I give you a definite answer because I'm not positive. But good question. Yeah, I'm not positive on that one. Yes, Eli.
So, since you have 12, but then if you try to bond it with like oxygen, with all the oxygens, that would be like you have 2 electrons per pair. Why? Because that's 2 forms. You have 4.
Oh, so it's not. So first off, everybody, and this is kind of what Ben asked, so you didn't hear. This right now has 12 electrons, right? In it shared 2, 4, 6, 8, 10. It's not up to 18 yet. It can get up to 18, but it's not there. We don't add anything. We don't have anything more to add. It's done. This right here is our picture minus one thing. Whenever something has a charge, you do have to throw brackets around it to indicate the charge. But no, you may not get, so 8 is that valence shell. But what starts happening is because the 3D shell is so close to the outside shell, those electrons in that shell can also start to bond. So they're not technically on the full outside, but they're close enough that they can bond as well to create this much bigger molecule happening. Yeah,
So
Connor and then Calvin.
Why can it bond with like inside electrons though? And like why is it that the outer S shell and the outer P shell are like why are those valence but the outer D shell isn't?
Because it's kind of an interesting thing of the definition of like what valence is. Valence electrons are considered the ones on the outermost level, right, distance-wise. But the 3D, just to give you an example, is in a sense, it's hard to like draw it because these things aren't simple drawings, but you could visualize it as like, so here's like your different rings, right?
Well, the ones with the 3D aren't they all metals on the outside?
The 3D orbital is very, very close to the 4p orbital in distance. And so it's technically an inner shell, but it has the capabilities of bonding still with other ones. But the one below it is too far away. Like, I guess our 4s would be like here. But the 3p is too far away to bond in that far.
What about the F shell? Can that do it too for like the one thing that it applies to?
Good question. I don't know for sure. I would say theoretically, yeah, it can. I don't know if it does, because you also start ending up with, the more things you start bonding to, all of a sudden the things you're bonding with can start fighting, like they're repelling each other as well.
Okay.
So you also just run out of space to bond, even if you have electrons that could still bond.
Okay.
So, Calvin, do you have a different question?
Yeah.
So I don't know why this is flashing.
How did you know that like the bromine and oxygen that it had a -1 charge?
Oh, that was just given in the formula. Yeah, so if something has a charge, it's just given to, but then our picture has to match what the formula tells us. So, yeah, Nora.
So how do we know that bromine has a full shell if it gets so like how will we know when it's complete?
Like, how do we know to stop? Is that what you kind of mean? Pretty much the way we know we stopped is once the outside atoms have their octet, the outside atoms can't expand. When something is an outside exterior atom, they don't expand ever. So technically in other cases, when bromine is on the outside, it doesn't expand its octet. Only the central atom will. So in this case, once I've done this, all my oxygens have their octet, I have to be done. And so this has to be what it looks like, because it's kind of the only way it works for all the oxygens to be satisfied with what they have going into it. So, does that make sense?
Yeah.
We'll do another example of an expand octet too. Yeah, Taylor and then.
I'm sure somebody asked this question already, but why is it phosphorus and not potassium that starts the adding electron shells?
Oh, okay. So it's because of so phosphorus is part of the 3p, right? This right here is the 3d.
Is it just so close that they're
Yep. And in the end, those are metals, so they don't actually covalent bond anyways, so they never really do it. So that's why we kind of just ignore the metals, because it's really all about the non-metal side. Because you gotta realize is even though the phosphorus doesn't have anything in its D, it can put things in it to bond with. Like, even hydrogen has a 7s orbital. It's just empty, right? All the orbitals are there. It's just a matter of if they're filled or not. So, yeah, Ben.
Is bromine in an excited state because its D orbital can bond? So does that mean it's not full, and so it has to be in an excited state?
So and we'll kind of, I think we'll hit it a little bit next time, if not in the next unit. If I'm understanding your question correctly, yeah. When certain things bond, they move into an excited state to be able to bond.
Mm-hmm.
So
that's why the D shells are empty and able to.
Wait, where are we?
okay, I don't care, somewhere. Okay, draw me a Lewis diagram of carbonate. And I'll try to get my screen from.
Like green.
An answer. If you don't want to know it yet, don't look up.
You have the wrong answer.
Oh wait.
Are these the three possible answers?
I think it's just written different.
Yeah, they're the same thing. They're just. And why is it written 2 and then negative?
So in chemistry, we put the charge after the number to signify the difference between a negative numerical thing versus an actual charge. it's fine. It's just a formality thing. But that's why I just have gotten used to writing it that way. Okay, if you have one of these three pictures, you can have 4 smiley faces. That's fine too. Yeah, that's fine too. Yeah, if you put your O on top, still works. Okay, questions first on this, and then I'll tell you what the real right answer actually is.
Great, I'm done.
I know, I'm so tricky. Yeah, North.
Does that mean that, like, one of the oxygen can't just evolve it for itself and have to have a shared name on it?
Because like the 2 extra electrons that you add, yeah, you wouldn't really just add it to 1 because then that gives it a full octet and you know it has to bond, right? So you'd give it to 2 different ones. And I'd say that's pretty typical with a charge. So when something has a charge, the electrons aren't being added to just 1 part of the molecule. It'd be like divided up. So, okay, eyes up here, everybody. Okay, so in the lab, okay, scientists discovered something about carbonate. So this is carbonate, okay? As they analyzed carbonate and measured its bond length. So there's a way in the lab where you can measure how long the bonds are, okay? I'm going to make up some numbers just to give you an example because I don't know what they are off the top of my head, okay? Scientists know, hypothetically here, that an oxygen to carbon single bond has a length of 100. Just go with me here, okay? An oxygen to carbon double bond has a length of 80. Because the more bonds, the shorter it gets. What scientists found about carbonate, though, is that all 3 of the bonds are 90. Anyone have an explanation for that? Jordan, what do you think?
Is it because, so like one has a double bond, so it would like pull it closer, but then there are 2 more already pulling on it. So if like, kind of like, if the bonds were ropes, you have one really strong one, but then like 2 weak ones, so it like evens out.
Love your thought, not right, because in the sense of the tugging, they're all the same thing. They all tug the same strength. But great thought, and thanks for sharing. That was my first thought. Connor, got a thought?
Does the double bond move around?
Yeah. So carbonate doesn't look like this, or like this, or like this. Carbonate is all 3 of them at once. The double bond does what's known as a process of resonating. The electrons are mobile. Say what?
It's like a metal, so electrons can
Kind of. And when things resonate, they sometimes develop certain metallic properties. That's why, have you ever heard of how anyone heard about carbon nanotubes before? They're super cool. But anyways, carbon nanotubes are super good conductors. But it's pure carbon. But it's because of this resonating idea, they can develop certain other like properties. So this idea of resonating, if this was the AP test and you had to draw a picture of like carbonate, your answer would have to be all 3 pictures with an arrow in between. This is designated as our resonating arrow. Now another way in which often, so there's kind of a few ways you can use. So you can do it that way, or you can do it like, well, I don't know. I don't know if we should do the second way because I haven't seen it on the AP test this way, but I'll show it to you and you can use it like on your homework if you want as like a shortcut. But I'd say like for AP testing to do it this way. But in organic chemistry, you can do resonating as like dashed lines.
Whoa.
See, that's easy. AP should accept that.
Trippy question mark?
I'll let you know. So this is how you're showing, hey, that double bond in a sense is everywhere. That's the weird thing is because they are moving so rapidly and so fast all the time, it really appears as if it's in all places. That's why the length of it is a blend of both of them. It's not 80, it's not 100, they're all 90. But it's equally distributed.
Shouldn't it be more toward 80 because if you average, there's like 2 80s
Probably.
and 100.
I just made up numbers to give an example. I'll show you some real numbers on another problem. But yeah.
How do you know if it's resonating?
Great question. Any thoughts? How would I know when I just draw one picture? Because this is what you drew, right? One of them.
Yeah.
After drawing one, what would be an indication of like, hey, this is gonna resonate? Connor?
The double bond could be in any of the places and it would be correct.
Kind of look like a mirror type thing. Like, oh, technically I could have put the double bond here or there. It's still all right. Another catch too is when you have a charge, you had to decide where to put those electrons. But you had 3 choices. So you could have put them here and here, here and there, here and there. That's actually a good chance that later on it's going to be resonating. Because those lone electrons are also kind of transitioning the process. So, great question.
Is this only with tunneling?
No, so a lot of different things resonate. We'll see another example here in a second. But
So can they only resonate when it has just one double bond? If like I had 2 double bonds in there, could they all resonate?
okay, I'm going to draw another color. So you're saying like if that was like that, could it resonate?
Yeah.
It could. It would only resonate what we would say twice. Because technically, like, it can go there,
But it can't go there, 'cause that.
but it can't go there. And so, but yeah, that could still resonate. So our bromate we drew earlier, if everyone wants to flip back that one, that BrO3 minus, that one actually does resonate twice. So, does that answer your question? Another way, so on your homework, guys, because I understand, if we understand this, it's just a little tedious to draw all 3. So you can use this to shortcut it on your homework, or I made up a shortcut that I let my like Gen Chem kids use as they're trying to understand this. So if you want to just like on your homework, draw one picture, and then underneath your picture, draw the arrow with how many times it's resonating. On your homework, that's fine. Like you don't have to draw all 3 pictures out because it's once you understand it, it's just kind of repetitive to keep drawing it. But yeah, Hunter, and then over here. Yep, I'll double check and see if I can find examples of this being accepted. It is true, like this is what you do in organic chemistry, so I would guess it would be. Just on all the answer keys I've looked at, it's always been more like this. So, yeah.
So
and-
with the BrO3, so since there's like 2 double bonds, could you draw like BrO3 and then dot lines between all of them? Or?
See, that's where it would get hard is with something like that.
Yeah, because it's like.
Because in a sense, that one with the measurements would have like, I don't know. Because that would make it appear as if it's going all 3 and it's not
Yeah,
going
it's
all
not.
3. So I would do like this type thing instead. I don't know how to do it with the dashed.
So, but like on the AP test,
You would just draw 2 pictures of that double bond in the different spots. So,
But couldn't it be in like 3 spots? Like there's 1 bond in this one, there's 1 bond in that one, and then there's 1 bond in this one. So would there be 3 pictures?
but if you think of the symmetry of it, so if like this is my bromate, right? So my other picture that I could draw could look like this, let's see here, like this, right?
Yeah, that's.
Technically, the third picture, let's see, would be double bond here,
The double bond, right? Right.
and then there.
Yeah.
So the thing is, in 3D space, like these 2 are the same thing.
They're just mirror it.
Yeah.
Because in like, yeah, so.
Okay.
But good question. Yeah, Matt.
I don't know how, or not how I didn't catch this, but what does resonating mean?
So resonating is the movement of electrons in a bond through different locations in the molecule. Think of it almost like I think you sometimes use the word resonating like in music with strings.
Yeah.
Like a string resonates, what is it doing?
It's like keeps moving.
It keeps
Yeah, it's vibrating, right?
Flash hands.
We're back to the flash hands again. Oh my gosh. This is like flash hands. So yeah, so it's like in a sense it's vibrating between all of them. And so it really looks like this.
Okay, so on the first 3
Yeah.
that you drew, 2 of the oxygens have 3 single pairs. Is that what they're called?
Lone pairs.
Lone pairs. But on the other one there, where are those electrons represented?
So let me show you this and tell me if this makes sense. If this makes you more confused, once again, forget it. But something you often do, once again, in organic chemistry is you do what's called pushing electrons, and you track where the electron's moving to understand molecules. So in a sense, you could kind of think of it like this. Okay, so like, once again, it's all happening at once. So it's really incorrect to think of it as one image, right? Because it's all happening interchangeably all at once. But to kind of understand the resonance, what you could say is, all right, so what happens here is that these electrons, let's see, so if the double bond's there, okay, so these electrons flip down, and in a result, they kick these ones out.
Okay, so you just don't write them?
They're just moving.
Well, I'm just saying you write it as those dotted lines.
Yes. It's like the lines get changed for dots, and then the dots get changed for lines, and so on
And
and so
does
forth.
it matter how many dots are in the dotted line?
As long as you have 8 around each, then not really.
No, I meant like
In the dotted
in the
line.
dotted line. So you have
Oh,
down there you
this.
have 3.
No, that's just dashed
Okay,
lines.
okay.
So yeah, these don't signify like how many electrons.
That's just
What they're
showing-
signifying is it's not a permanent bond. That's our, what do we call it, flash hands sign?
Yeah.
So that's like the momentary bond that's always there. So, yeah, listen.
So how does having like the resonance change the properties of the molecule?
So what it does is, one, it causes a lot of symmetry. So rather than being like unequal, it's a symmetrical thing, which next time we'll relate it to polarity, and that can affect sometimes if something is polar or not, is the symmetry of it. So, great question. Yeah, Andrew?
So, I guess this is just kind of like a little hypothesis.
Yeah.
But because the electrons are moving around in bonding,
Yeah.
kind of like a metallic, is that why they've become more, have metallic characteristics? Is because they just are bonded in the same way that metals are?
Because in order to have, like, the reason why metals have their properties are because of those free-flowing electrons. And resonance provides somewhat these free-flowing electrons. Yep, exactly.
Does that make carbonate valuable?
No, good question though, because it's not all its electrons aren't mobile, right? You have 3 bonds that are very solid and rigid. So in terms of bending, nope. But in terms of other properties, yes. So good question though. Okay, last thing dealing with Lewis structures is this thing known as a formal charge. Formal charge is simply a systematic way to test if a structure is plausible. Because sometimes you can draw it on paper and it may all have an octet, but it's like, okay, well, which one is right then? If everybody's happy, why would it bond this way and not that way? So formal charge is a way to check it. Now I'm going to write the official equation, and then I'm going to write a simple equation, okay? So the official equation, you take the number of valence electrons in an atom, subtracted 1/2 the bonded electrons minus the lone electrons. Yeah. Yeah, this is one that's not on your formula sheet. I know most of them are, we haven't got to it yet, but here's a simple way I think about it though. So you take valence electrons, subtract the lines, subtract the dots. Okay? So for example here, carbon dioxide can be drawn in either form. This way or this way. If you count up their octets, they're both happy, right? 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Same thing, 8, 8, 8. So the question is, which one is the right one? Formal charge is a way to check that. So how many valence electrons does oxygen have? 6. So we're going to take 6 minus lines. 2 lines. How many dots? 0. Okay? Formal charge wants to be at 0. Okay? Carbon has 4 valence electrons. Minus 4 lines. 0 dots. Is that 0? Same thing over here. All 0. Obviously, that would mean that this is the correct structure. But to compare, let's calculate it over here. So 6 electrons minus 1 line, minus 6 dots, negative what?
Where are you getting that from?
The 6?
So this one is dots,
The number of elements.
So the 6 is the number of electrons in.
and this is the number of lines. So there's 1, 2, 3, 4, 5, 6 dots, and then the 1 line. Ready? Help me with this one, Calvin. How many valence electrons does this one have? Good. How many lines are around it?
Are 400, because it's got the 4 lines.
So 4 lines, and how many lone pairs?
Which is
0. So carbon is at 0. But this oxygen, so we have 6 again, minus how many lines? How many dots? Plus 1.
I think we.
Does that make sense?
Yeah, now
So since these are not at 0 and this gives us a 0 configuration, that's why that's the true structure of carbon dioxide, not that structure. Yeah.
So why do they do this naturally? Why do they like prefer that one over the other?
What formal charge tracks is like this. It's a way to help kind of track the stability of how they bond. And so formal charge isn't an actual charge of anything. It's just a systematic way to check its stability. And so this tells us, hey, this is more stable than that. And so they always exist in the most stable form they can. So,
So
oh yeah, go ahead.
could they potentially exist in that form if we like put a bunch of energy into it?
I guess so, but you'd have to also like,
Would it change properties?
I think it would always go back.
Yeah, it would always just
Yeah, yeah.
Would it change properties though?
unbond.
It could, because structure does determine properties a lot. So, yeah, Alyssa.
So with the molecule, if there wasn't a formal charge for the molecule that was 0, would it be satisfied with something similar to that?
Good question. So, in this example, calculate the formal charges of these 3 different ones, and we're going to find that none of them are 0, 0, 0. So you guys do that really quick. So find the formal charge of each element in each of those molecules.
Are these guys?
Are they polar covalent?
Yeah, like one, or
How do we-
like one's closer because like you have a triple one on one side and one.
So the number of bonding doesn't actually affect polarity. Polarity is all about who's in the tug of war.
Oh, the bigger guy.
Yeah. Yeah, but it actually doesn't matter how many ropes you're having a tug of war with. It's all about who's pulling harder.
Okay, so you just say, okay, so atomic rate this, to figure out.
Yeah, we were just looking more at which one has a higher electronegativity. So, a great question. Yes,
Does
Sam?
that negative sign change anything?
Not in terms of formal charge, no. Yeah, good question. Okay, I'm just passing out your homework assignment, or one of them for tonight.
One of them?
So you just have this homework paper, it's a bunch of Lewis structure practice. So lots of pictures to draw. And then there's just 2 quizzes on AP Classroom. Now,
It's not pretty.
keep in mind, this all isn't technically due until next Tuesday, because that's when I'll see you again. Either do that,
I'll just bring my whole.
like do it right when you get home today, then you don't have to worry about it. Or don't forget about it until next Monday night. Now, here's the question is which one holds that negative one charge? That tells us which structure we want.
I don't know how. Let's not talk about it. That was I literally
Okay, so that's what I got for my formal charges, everybody. So right away we throw C out because it has the least amount of zeros. Now the question is, it's just a -1. In this one, the -1's on S. On this one, the -1's on N. the one that has the higher electronegativity can handle the excess charge better. N has the higher electronegativity. So this is our structure. Okay?
Sorry, what's the difference between, sorry.
The negative is on nitrogen versus on the sulfur. Because the more electronegative one is the one we give the extra, because this was an extra electron, right? So it should go to the one with the higher electronegativity.
Duncan, Jeremy, Alex,